Hello everyone. I wanted to do a very quick and dirty explanation of the dice kinetics lab because we had lab today and quite a few people were very confused. And I don't think it helped that I got this up there on the Blackboard site late. And I apologize for that. So I'm going to go ahead and do a quick example of what you're supposed to be doing with the Excel sheets and with the data and creating those graphs. So obviously you should be doing all of this yourself, but you can essentially copy what I'm doing here when you go through and do this. So for the first part, for trials 1 and 2, we are pretending like we have a whole bunch of die that we are rolling and pulling out the 6s for trial 1 and then 5s and 6s for trial 2. So I'm going to use the maximum number of die here just to show you the maximum amount of time that it can take, the maximum number of rolls that it might take to do this. So if I have 600 here, that means I have 600 different die here, and I can push let's see, F9, and it rolls it again. And so what I have here is it just picked a random number between 1 and 6 for each of these 600 spots. And we do not have to go through and count all of these, thank goodness. Instead, what we're going to do is we're going to look here at what it has tabulated for us. So it says that we have, actually, let me do that again. I don't want it to be exactly correct. Okay, there we go. Because 100 would be exactly 1/6. I don't want it to be quite that pretty. So we have 111 dice that rolled a 6. And so what I'm going to do over here in my separate worksheet that I have set up, I have the roll number, and it might not go all the way to 30. I just picked 30 randomly. I have the reactant dice, which right now are all set at 600, because what I have here is inside of here in this cell, I have it set up where this cell is equal to the cell above it minus the cell next to it. So what I'm going to put here is 111, because that is the number of dice that it told me reacted. So if I do that, it automatically adjusts, and it tells me that I now have only 489 dice that are still reactants. Those that rolled a 6 reacted. They are no longer reactants, they are products now. And so I only have 489 left, and so that's what I'm going to put here, 489. Do that, and it rolls again, and it tells me that 80 of them reacted. So I'll go back over here. This is 80. Now I have 409 left. Back over here. 409. 65 reacted. Back over here. 65. 344. So we're just going to go back and forth here, putting in the number of die that we're rolling, and it will tell us how many roll a 6. So 59, so I have 285 left. 37 react. So I have 248 left. 44 react. So I have 204, 46, so I have 158, 26, 132, 22, 110, 19, and I think I'll call it here. So I have 91. Now you, doing this at home, I do want you to still go ahead and go down to where you have 10 dice left. So I'm going to go ahead and stop it here. So I had 11 that reacted there. So I'm just going to stick with this data because I don't think you want to see me go through all the rest of those. So we'll just stick with this data for now. But again, you would go ahead and keep going until you get to 10. Don't go past 10, because even when we get close to 10, the statistic starts to break down. So with this data here, the rolls are essentially taking the place of time in our kinetics. The reactant dye is the concentration. It's how much of the reactants are still in our mixture. And so if you remember, first order kinetics is the natural log of the concentration versus time. If you plot the natural log of the concentration versus time, you will get a straight line. And so what we're going to do is we're going to show that that is the case. We're going to show that when you roll dice, you get first order kinetics. That is a first order kinetics situation, where you just have a certain raw probability of the thing that you're interested in happening every, in this case, every roll, or in terms of real life, for every period of time that you're concerned with. And so we're going to go ahead and make another column here that is, actually let me put it down here. So this is going to be equal to ln of that column. I'm going to take the natural log of that, let it do the math there, and I want to insert a scatter plot. So I'm going to select the data here. Let's see, we should have for our x number of rolls, and for y the natural log. And what do you know? We got a relatively straight line. So this is the chart that I'm looking for here. This is the first order kinetics. If you wanted to make sure that the second order or zero order did not fit better, you could go ahead and plot just the number of reactant dice versus the number of rolls, and 1 over the number of reactant dice for number of rolls. But I don't think the lab actually asks you to do that. I thought that it did it first, and so I think I told someone in lab today that they were going to do that, but I don't think it actually asks you to do that. The person that wrote this lab, he's over at Metro Campus. He tweaks it like every semester, and usually taking stuff out. So I don't think that you actually have to do all 3 of those, but read through the lab carefully and you can correct me if I'm wrong on that. But you're going to do the exact same thing that we did here for trial 2, only in trial 2 you're going to be using the dice that rolled a 5 or a 6 number, but everything else is exactly the same. So you're going to be using the larger numbers, so it should go even faster for trial 2. For trial 3, what we're going to do is kind of similar to trial 1 and 2, except now we have all of our reactants on one side, and we're going to have the products going back to being reactants as well. So we're going to have a forward reaction and a reverse reaction. So for example here we're going to start with 250 reactants, and we might as well just stick with the 250. So I'm going to go ahead and tell those to roll, and so it tells me that, and I'm going to go with the 5 and the 6 for the reactants, because I believe that is what you're supposed to do for this trial. So 5 and 6, we had 85 that reacted. So I'm going to put that right here, and I had 0 products that reacted, because I didn't have any products in the first place. So, oh, I almost forgot actually. I'm putting 0 here for both of those. So it was 85 and 0. There we go. So this first row is just for the initial state, essentially. So now that I have put in my 85 that reacted, now it's telling me, okay, now I have 165 reactant dice left and 85 product die. So I'm going to go back over here, and it was 165 and 85, if my memory serves me. And so with those numbers put in, it's now telling me that in the forward direction I had 61, and in the reverse direction, which I'm only using the 6 for, so only a 6 can react going in the reverse direction, it's 19. So 61 and 19. Let's go back over here. 61, 19. Okay. So notice here that the way I have this set up, the reactant dice automatically adjust, because I told them that each of these is the cell above it minus this cell. Those are the reactants that are reacting, plus the products that are reacting. And this cell is just the opposite. So the product die, it's the cell above it, plus this cell minus that one. So you're subtracting the ones that it's losing and adding the ones that it's gaining. And if you didn't quite follow that, feel free to pause the video here and look at my equation for each of those, and that should help you get straightened out. So where were we? So now we have 123 and 127. So going back here, 123, 127. And I get 41 of these reacted and 18 of those. Going back again. Oh, I forgot that was it 43 or 41? 41 and 18. Okay. 41 and 18. So now I'm at 100 and 150. 100, 150. So I'm at 25, 22. 25 reactants, 22 products. And oops, if I get the numbers. So I'm at 97, 153. So 97 and 153. So I have, big number this time, 42 and 25. That's going to throw it off a little bit. 42 and 25. So now I'm at 180 and 170. 108, what, did I do that right? I did something wrong there. 80, not 180. 80 and 170. Yeah, don't do that. So 80 and 170. So now I'm 24 and 37. 93 and 157. 3325. And I'll just do a couple more of these. So let's see, now I'm at 85, 165. 85, 165. So 30 and 27. 82, 168. 26 and 30. This will be the last one that I do. So 26 and 30. So the last ones here, 86 and 164. 86, 164. So we get 25 and 25. Hey, that's a good one to end on. So now, again, you would go ahead and fill out the whole thing. It does specifically ask for 20 iterations, but just for the sake of time, I'm going to stop it there at 10. So what you're going to do here is, and I wonder if it'll work out if I just do it like this. If it'll work. Hey, it does. Okay. You're going to have a chart like this, where the series 1 here, that is the product die, And so you can feel free to go in here and add labels to those. Oh, that's not what I wanted. Not that kind of label. Let's see. Yeah, so you can go in here and add chart elements, and you can add in the proper names for those. But Series 2 is the product die. Series 1 is the reactant die. You can see we started with only reactants and no products. And then at about, I would say, maybe even row 4, we had practically reached equilibrium. Maybe even row 3, we got to equilibrium. Because you notice here, around 3, 4, 5, somewhere in here, it pretty much doesn't change anymore after that point. And you should see just this same overall pattern continue out for the last 10 iterations, where you have, even though the products require a 6 to react and reactants only need a 5 or a 6, you still have the same number of dice going in each direction because you have more dice that are in the products side. And so just because you have more of them, you end up having the same number, roughly, that react as the reactants do. And that is really the essence of an equilibrium, where you have two reactions, one that is more favorable than the other, but because it has more stuff available to react, it's able to go just as fast as the one that is, energetically speaking, more likely to happen. So this is just a very quick example of how to set up the Excel sheets and make the graphs and analyze those graphs. So just real quickly here again, this is what the equilibrium should look like. You're going to be doing products over reactants to find your equilibrium value. And so that would be literally just taking the average of a few of these data points for the products and the average of a few of the data points for the reactants. Products divided by reactants, that'll give you your equilibrium constant. And then for parts 1 and 2, the slope here, or more specifically the negative of that slope, is your rate constant, which should, hopefully, be very close to 0.167, since that is 1/6. And the rate constant is just the likelihood of the molecules reacting in a certain period of time, which in our case would be per roll. So it should be a 1 in 6 chance for the first trial, anyway. A 1 in 6 chance of the reactant dice reacting in that one roll. Alright, I hope that is helpful. Let me know if you have any other questions, and I will see you all in lab or in Collaborate. Good luck.